So we're going to be talking a little bit about light, in other words, electromagnetic waves, so EM waves. And when light strikes a boundary, there's a couple things that happen. Just like any other kind of wave, some of the light is going to be transmitted across the boundary. So some of the light gets transmitted. And some of the light gets reflected. Okay, so I want to draw you a little diagram of both of these phenomena. And before I do that, I just want to talk about what a boundary means in the context of light. Well, a boundary in the context of light could be the boundary between, for example, the air and water. Right, let's say there is ambient light that is striking the surface of your pool. Okay, so here we have a boundary, in other words, what I'm going to call an interface. Okay, so an interface is just the boundary that separates medium 1 and medium 2. Okay, well, our incoming light we are going to refer to as our incident ray. And this incident ray is what we're calling sort of the source of the light. So the light, let's say maybe I have a laser situated right at this position. Okay, so that is where the light is coming from, and this is the trajectory of that light. Okay, so the light is going to strike the interface. Well, anytime we talk about the angle at which it's striking the interface, we always talk about it relative to this imaginary perpendicular line called the normal. Okay, so we refer to this reference point, or this imaginary perpendicular line, which sits 90 degrees from the interface. We call this the normal, okay? So wherever that incident ray is striking, the angle that's going to be measured is always going to be measured relative to the normal. In other words, relative to if we were to just shine our light directly on the normal or straight on into that interface. Okay. So anyway, as I said before, when light strikes a boundary like the one we've shown between air and water, some of the light gets transmitted, meaning some of it's going to pass through into the water. Okay, well, if we're shining that light at an angle, actually what's going to happen is the light is going to bend, and it could bend in either direction. It might bend closer to the normal, like I've shown. As you can see, this theta, or this angle here, is much smaller than this angle. As you can see, again, I'm measuring it relative to the normal. Or it can bend away from the normal, meaning theta in medium 2 is greater than theta in medium 1. And we're going to talk more about that phenomena, which is called refraction, in a later video. So as you can see here, some of the light is going to be transmitted. So let's call this our transmitted ray. Okay, and as I said before, some of the light gets reflected. So not all of this ray is going to pass into our new medium. Some of it is going to bounce off the boundary, like any other wave. And it's going to bounce off like such. Okay, so here is our reflected ray. So what I've just shown, without really saying so, is something that you already sort of intuitively know, and that is called the law of reflection. So the law of reflection essentially states that the angle of incidence will be equal to the angle of reflection. The angle of incidence will be equal to the angle of reflection. Okay, so this can actually be represented by a formula which says theta I, or the angle of incidence, equals theta R, or the angle of reflection. So I'll draw a little diagram here. Let's say we have a mirror, and if this is our mirror, we should also draw our normal, because anytime we have any sort of boundary, it's really important that the way we are measuring our angle of incidence is relative to the normal. So label the normal. Okay. So let's say we have an angle of incidence. So here's our incident ray. And let's call theta I. Let's say it's, well, it looks about maybe 40 degrees. So theta I in this case is 40 degrees. Well, if theta I is 40 degrees, then based on the law of reflection, we're going to see theta R is also 40 degrees. Okay. Sometimes the Regents curriculum likes to trick you, and so they'll do something like such, where they'll give you this kind of information. They'll tell you, actually it's a terrible drawing, sorry, forgive me. I haven't had much practice lately. Okay. That is such a bad drawing, I can't even, sorry, I'm like holding my phone, so like things like this happen. Okay. So let's try that again. Much better. That actually looks like something. Okay. They'll give you information like this and say, oh, hey, this angle right here is 20 degrees. Tell me the angle of reflection. They'll draw the normal for you, or maybe they won't. So what is the angle of reflection? Okay, what is theta R in the diagram I just showed? Well, the first thing you need to realize is, well, first of all, we know the law of reflection says that the angle of incidence equals the angle of reflection. So you might be saying to yourself, oh, 20 degrees. Well, it's definitely not 20 degrees, and the reason is our angle of incidence is not this angle right here. This is not the angle of interest at all. What is the angle of interest is the difference between 90 degrees and 20 degrees. In other words, our angle of incidence here is actually 70 degrees, and that tells us that the angle of reflection is going to also be 70 degrees. So in this case, theta I is 70 degrees, therefore theta R is also 70 degrees. And they might have you draw the reflected ray, and hopefully your skills are not as terrible as my own, and you would draw it as such. Theta R equals 70 degrees. Okay, so the law of reflection is pretty straightforward, but I do want to show you the difference between diffuse reflection and regular reflection. So let's do that all the way up here so that I don't waste paper. There is a reason why you cannot look at yourself in a piece of paper, even though you can clearly see the paper, which means we know that light is actually bouncing off of it. So there is diffuse reflection versus regular reflection. Well, when you look into a piece of paper, diffuse reflection is happening. So here's an example. Try looking at yourself in a piece of paper. You can't, even though light is bouncing off of the paper and bouncing off of you. Try looking at yourself in a piece of paper versus regular reflection, which, as an example, try looking at yourself in the bathroom mirror. Okay? The difference is, in diffuse reflection, you might have a surface that is actually very irregular. So I'm going to do my best to draw a really irregular looking surface, which you would find if you looked on a microscopic level at a piece of paper. Okay? So here is a paper under a microscope. Paper. Okay? Now, what you will notice with a piece of paper is as the light strikes it, let's say we have a light source right over here. So let's say we get these nice little light rays coming in. Do my best to do a good job with this. So, I don't know if I'm really gonna... Okay. Okay, so let's say we just have these light rays like this striking the piece of paper. Well, we know that at each successive point, the reflected ray can only be done when we first draw the normal, or the perpendicular line relative to the surface at that point. Well, at this point of the paper, the normal is sitting like this. So for this first incident ray, when it gets reflected off, it's going this way. Well, let's look at our next point. Well, here's our next point, and our normal is almost exactly vertical. So in this second position, the incident ray will produce this kind of a reflected ray. Well, let's look at this next position over here. As you can see, once again, our normal is kind of going this way at this point. So here's our incident ray, which means here is our reflected ray. And we can continue on. I will do this last point. This one's a little bit skewed over here. This one's a little more vertical, and so we get another reflected ray coming like this. But what you'll notice is that all of the reflected rays, so we have one over here, we have one over here, we have one up here, one over here, they're all going off in different directions, and that is characteristic of diffuse reflection. On the other hand, with regular reflection, we actually have a smooth surface. What that means is, if we have incident rays coming in from a source, at each of those points, the normal is going to be parallel to each other. And what that means is these rays will all be reflected off at the same angle, and those will produce a uniform image.